today's episode, we're going to be looking at how we can apply the chain rule to any kind of equation. No, I'm not saying function, but any type of equation. Now, we know the chain rule as being the derivative of f of g of x. When we have a function inside of another function, is the derivative of the outside, keeping the inside the same, multiplied by the derivative of the outside. Applying this in some cases, if we have d dx, the derivative, the rate of change of this function with respect to x, well, I've got d dx of this function squared. Well, f of x is inside the square function. So we know that we would apply the chain rule, we'd multiply by that exponent, keeping that interior the same. Notice 2 subtract 1 gives me an exponent of 1. I don't need to write that. But also then multiply by the derivative of the inside, f prime of x. Now, f of x typically we use when we're talking about algebra. When we're talking about geometry, f of x is really equivalent to just being y. So then if you think about d dx of y squared, well, y is just like f of x. So d dx, the derivative of y squared, or the rate of change of y squared with relation to x, is exactly the same as f of x squared when we take the derivative. We would have the derivative of the outside, 2y to the first power, multiplied by the derivative of the inside. The derivative of y would be dy dx, just like when we have f prime of x. That is saying, well, d dx of y, that is the rate of change of y with respect to x. That's our slope. That's our rate of change. That's our derivative. Now, we could also think about, okay, taking d dx of x, aren't we going to have dx dx? Well, yeah, that follows because we would apply the same thing, and the derivative, or the differential, is an operation that we apply onto an equation. dx dx, well, that's dividing by itself. It's the rate of change of x with respect to the rate of change of x would just be 1. Notice it's exactly how we've done things before. So we're going to take this and apply this in a sense of what we call implicit differentiation. Let's consider this equation, x squared plus y squared equals 25. That is the equation of a circle centered at 0, 0 with radius 5. At any point on that circle, we can find the equation of the tangent line, or rather, the tangent line exists through any point on the circumference of that circle. But can we find the slope at that point? Well, taking x squared plus y squared equals 25, we cannot solve it for just y. It's not a function. But we can still find the equation of a tangent line at any point of the circle. So there has to be some derivative or slope at any point. This is going to require what we call implicit differentiation. Rather than having an explicitly defined function like f of x equals, we're going to have an equation that relates x and y in some way. And we're going to take the derivative. We're going to apply the differential operator d dx to the equation. Another example, x squared plus y cubed equals 6xy. That's known as the folium of Descartes. Now that curve, clearly that's not a function either. But at any point along the way, there exists a tangent line, and we should be able to find the slope of the tangent line, or the derivative at that point. It's not a function, but when we have such an equation, we're going to apply implicit differentiation. It's a function, it's an implicit definition, so we're going to apply implicit differentiation because our function is defined in terms of itself. That y is really the same thing as f of x. Well, if it's x cubed plus y cubed equals 6xy, that's just like having x cubed plus f of x cubed, where f of x is a function in terms of y, a function in terms of x, f is a function in terms of x, y is an equation, it's related to x. So we're going to use this implicit differentiation to find the derivative of the equation in terms of actually both x and y. So let's see how this works. Let's find the derivative of x squared plus y squared equals 25. I'm going to take d dx of that entire statement. So I'm applying this operator to my equation. And the way this distributes, but I'm thinking, okay, I got to take the derivative of x squared. That's going to be 2x. Take the derivative of y squared. We saw that already. d dx of y squared, that is 2y multiplied by the derivative of the inside, multiplied by dy dx. So this is plus 2y multiplied by dy dx equals 0. We have, based upon our chain rule, there is still a y in our derivative. 25 is a constant, so that gives us 0. And what we want to do is we want to solve for dy dx. I notice that everything is a multiple of 2, so I've got x plus y multiplied by dy dx equals 0. I'm going to subtract x, having y times dy dx equals negative x, and therefore dy dx equals negative x over y. The rate of change at some point depends on both x and y. it's going to be the negation negative x divided by y. So let's think about finding the equations of the tangent line to the circle at that point. We now have that the derivative, the rate of change, the slope at any point is equal to negative x over y. So if I have the derivative dy dx evaluated at the point 3, 4, that is going to be negative x over y, negative 3 over 4. Our tangent line, y minus y1 equals m x minus x1. I'm going to keep on using point slope form. We have y subtract 4 equals our slope, negative 3/4 x subtract 3. And thinking on our circle, 3, 4 is there, and it makes sense that we would have a negative slope for that tangent line. We used implicit differentiation. I'm taking the derivative of an equation, not a function. In short, anytime I see a y, we're going to multiply by dy dx after taking the derivative of that statement. That's the chain rule. Let's do another. So let's find the derivative, the dy dx for x cubed plus y cubed equals 6xy. I'm going to apply the derivative operator to my equation. X cubed plus y cubed equals 6xy. I'm going to take the derivative of x cubed, giving us 3x squared. To take the derivative of y cubed, giving us plus 3y squared, chain rule multiplying by dy dx. I'm going to apply the derivative to 6xy. Ooh, that's the product rule. And I'm going to take this as 6x multiplied by y. So this equals the derivative of 6x is 6 times the second y plus the first 6x times the derivative of y, which would be dy dx. Product rule. What I see here is we have dy dx in two different locations. We're going to group those and then factor dy dx. That's going to come up top. I'm going to have 3y squared dy dx subtract 6x dy dx equals 6y subtract 3x squared. So you saw that I subtracted to group the dy dx terms. We're going to factor then. So we have dy dx equals, that is 6y subtract 3x squared divided by 3y squared subtract 6x. And I notice that everything has a factor of 3, so this is equal to 2y subtract x squared divided by y squared subtract 2x. We have our derivative at some point in terms of both x and y. Next, let's find the tangent line to the full name of Descartes at the point 33. We have our derivative above, so dy dx. We're going to evaluate at 3, 3. It's going to get us 2 multiplied by 3, subtract 3 squared. I'm plugging the point 3, 3 into our derivative equation above, divided by 3 squared, subtract 2 times 3. So that gets us negative 3 divided by 3 gets us negative 1. Our tangent line, y subtract y1, 3, equals the slope, negative 1 multiplied by x subtract x1, x subtract 3. At what point in the first quadrant is the tangent line horizontal? Let me think about that. Horizontal, that would tell us that our slope is equal to 0. So our slope, dy dx, is going to be 0. And that, let's just get that down there, is 2y subtract x squared divided by y squared subtract 2x. Now if I cross multiply, that's going to give us 0 equals 2y subtract x squared, or y equals 1/2 x squared. So what this tells us is our slope is going to be equal to 0 when we have that relation. Let's plug that point back into our initial equation. We've got x cubed plus y cubed equals 6xy. We have y is equal to 1/2 x squared. So I'm going to substitute that back into the initial equation, giving us x cubed plus 1/2 x squared cubed equals 6x 1/2 x squared. So we have x cubed plus 1/8 x to the 6th equals 3x cubed. I've got 1/8 x to the 6th subtract 2x squared cubed equals 0. And factoring, 1/8 x cubed, that'll leave me with x cubed subtract 16 equals 0. So looking at our factors, that would be x equals 0 as a solution, which is not in the first quadrant. It's on an axis. It's actually the origin, but it's not in the first quadrant. And this would give us x equals the cubed root of 16, which is 2 raised to the 4/3 power. That's our x value. If I want to find our y value, because we want to find, back up top, our point, I can either take that x value and sub it in to our initial equation, or, whatever's easier, I can sub it into the derivative. Ooh, that definitely looks easier. So I'm going to plug it into the derivative. We've got y equals 1/2 x squared. So substituting in that coordinate y equals, that's 1/2 is 2 to the negative 1. I've got 2 to the 4/3 raised to 2. So y equals 2 to the negative 1 multiplied by 2 to the 8/3. And so we have y is 2 to the 5/3. We've got this coordinate then, this point where our tangent line is horizontal, 2 to the 4/3, 2 to the 5/3. I would encourage you to use Desmos to actually verify that that is a point in quadrant 1 where the derivative is 0, where the tangent line is horizontal. Let's try another. Here's a monster of a problem. Sine of x plus y equals y squared plus cos x. Now initially I see, oh, that's the chain rule, because I've got an external function with an internal equation, and then we also have the product rule there. I'm going to apply the derivative operator, d dx, on sine of x plus y equals y squared multiplied by the cosine of x. Derivative of sine is cosine, keep the interior the same, multiplied by the derivative of the interior, which is 1 plus derivative of y is dy dx, equals y squared times cosine x. That's going to be the product rule. So we have the derivative of y squared is 2y multiplied by dy dx times cos x. Add to that y squared multiplied by the derivative of cosine, which is negative sine x. I'm going to distribute on the left cosine of x plus y, because that's one term. I'm going to multiply by 1, multiply by dy dx. And then I'm going to neaten things up. So we've got cosine x plus y plus cos x plus y multiplied by dy dx equals 2y cos x times dy dx, subtract y squared sine x. Now we're going to group those terms that have the dy dx, get everything else on the other side. So we have cos x plus y, fix that, add to that y squared sine x equals 2y cos x dy dx, subtract cos x plus y dy dx. So I added, subtracted, factor, that's cos x plus y squared sine x equals 2y cos x subtract cos x plus y multiplied by dy dx. Be extra careful with your parentheses, and then we'll divide. We've got dy dx equals cosine x plus y squared sine x, all divided by the other statement, 2y cos x minus cos x plus y. Too bad. Last one that we've got, we're going to take the second derivative. Well, to get to the second derivative, first, we're going to take the first derivative. So I'm going to apply the derivative, dy dx, on x to the fourth plus y to the fourth equals 16. We have 4x cubed plus 4y cubed multiplied by dy dx equals 0. I notice that everything is a multiple of 4, and then I'm going to subtract and divide, giving us dy dx equal to negative x cubed over y cubed. Now, I'm going to rewrite this as negative x cubed y to the negative 3. Reason for that will be apparent when I take the second derivative. It's going to be a little bit easier. I'm going to use the product and the chain rule here. Now that we've got the first derivative, dy dx is equal to negative x cubed y to the negative 3, we're going to apply the derivative to this equation. So I'm going to take d dx of dy dx. That's going to give us the second derivative, d squared y over dx2. That's the notation that we have to indicate the second derivative. Now, I noticed the product rule here. So we're going to take the product rule here. The derivative of the first is going to be negative 3x squared, keeping the second the same, y to the negative 3. Add to that, we're going to keep first the same, negative 3x squared, multiplied by the derivative of the second, which is negative 3y to the negative 4, multiplied by dy dx. Now, dy dx, we know what that is. dy dx is equal to negative x cubed times y to the negative 3. So we can actually sub that equation, sub that statement in for dy dx. So we get the second derivative of y over dx squared. It's negative 3x squared y to the negative 3. I see there are two negatives there, so I'm going to factor that. Give me plus, that is 9x squared y to the negative 4. Is that coming in? Multiplied by dy dx, which is negative x cubed y to the negative 3. I'll simplify this from here. So we've got d squared y over dx squared. The second derivative is negative 3x squared y to the negative 3. We have subtract 9x to the fifth y to the negative 7. There's our second derivative. Now, if you came up with something using the quotient rule back from the start, you would get the same thing. You would come up with an equivalent statement. It might look a little bit different, but it is an equivalent statement. Sometimes the chain rule can be applied and the product rule instead of the quotient rule. Nice little trick. There we go.